So let's start with single slit diffraction. We start with a single slit with W, and we're going to illuminate it with a plane wave. Each point on the plane wave can be thought of as its own emitter. And when that plane wave encounters an aperture, these emitters are now isolated, and they're going to begin to diffract and diverge. We want to find out what that angle of divergence is. Now, spoiler alert, that aperture forms a rectangle, and propagation in space is like a Fourier transform, so that in the far field, that rectangle of light turns into a sink of light, or sink squared if we're looking at intensity. So to find the divergence angle, the angle from the center of the sink squared to the first null, we're going to look at rays inside the aperture, in particular from a pair of points separated by W over 2. Now we could have chosen any pair of points separated by W over 2, but we'll stick with this first one in the center, or one at the top edge, or perhaps one at the bottom edge. Now, the rays emanating from the points at the center and the bottom, we're going to say, are traveling straight ahead. That means they're in phase with each other. And their crests are constructively interfere. Now, as we compare the points in the center and the top, we're going to say that these are at some angle at which these wavefronts destructively interfere. That is to say, that crests fall on troughs and they cancel each other out, and we expect that angle to be dim, to be dark, to be the null angle. So we want to find out what theta is. We can do that by drawing a triangle where the opposite side is lambda over 2 and the hypotenuse is W over 2. Thanks to a 90-degree angle, the little theta there is exactly the same as the big theta, and we can write the expression sine theta is equal to lambda over 2 all over W over 2. The 2's cancel out, and we get our final expression, sine theta equals lambda over W for a single slit. Theta to the first null. Now let's look at the double slit diffraction case. This is a lot like what we had before. In fact, we're going to keep an aperture size of W. It's just that now we have 2 of them, separated by some distance d. And believe it or not, they're still going to make something like a sink or sink squared if we're looking at intensity in the far field. And that angle, theta, where sine theta equals lambda over W, that's still true. For this sink envelope, and that here is the difference, there is another pattern here in the far field, and it is a cosine in amplitude or a cosine squared in intensity, and it is multiplied by that sink or sink squared envelope. Let's talk about why it is that we have a cosine multiplied by a sink. This is a result of the Fourier transform. So Fourier transform is taking x, transforming it to k space or theta space. What we have are 2 rectangular apertures. That's the same as 2 impulses convolved with a square in space. And the Fourier transform of 2 impulses is a cosine, if they're symmetric. And the Fourier transform of a square is a sink. And that convolution function in space is going to turn out to be a multiplication in spatial frequency. the result of the multiplication of the cosine and the sinc is just what we talked about before. Cosine multiplied by sinc envelope. Now what we're going to try to determine today is a new angle. We want the angle between the highest intensity point and the first null. This is basically the beam width for that central diffractive blob. Maybe we'll call it phi to disambiguate it from the theta we had before. We're going to find this angle just like we did in the single slit case. We're going to choose a pair of points. We're going to draw a ray emanating from them. The rays going straight are going to be in phase, just as they were before. But we're going to try to find an angle at which two rays can be drawn and they're going to be out of phase. Fun fact, if d is small, this angle is going to be large, and if d is large, this angle is going to be small. So we find some theta where we get destructive interference. Now we can draw a triangle just like we did before, except the opposite this time, and the opposite this time is again lambda over 2, the angle is phi, and the hypotenuse is d. So sine phi in this case then is lambda over 2 times d for the double slit. Okay, now let's talk about multiple slit diffraction. Now, instead of 2 slits, we're going to have many slits. Like before, they will have a width of w, which means that we're going to have an envelope that is a sinc function, or sinc squared for intensity. The length over which we'll have these slits we'll call L. And we're going to go ahead and just pretend that this is just like our original single slit case. We're going to choose some slit here in the middle, and we're going to have a point there. We're going to choose some slit near the edge, and we'll have a point there, and this will be our pair of points. And we're going to look at the far field at a bunch of sinc functions multiplied by a big sinc envelope. That is what the result of having multiple slits is in the far field. One sinc multiplied by another, and we're going to look to see this super narrow angle right here, which we'll call phi again. Again, looking to see what the resolution is of this grading function. And all we have to do is look at these two spots on our grading, run exactly the same argument as before. Going straight, they're in phase. Going not straight, at some angle, they're going to be out of phase. That's going to happen when this is lambda over 2. This side is L over 2. This angle is phi. That tells us that sine phi is equal to lambda over 2 over L over 2. 2's cancel out. We get a lambda over big L. So, if we want to know what the resolution of these diffracted orders in the far field is going to be, they're going to get bigger, thicker, with increased wavelength, but they're going to get thinner with increased interaction length, with increased grading length. The bigger your grading, the more narrow and pointy your diffracted orders. This then is going to be our multiple slit equation. All right, now we're going to give all that we've learned some practical application in the field of acousto-optic modulators. Acousto-optic modulators are usually a piece of crystal or maybe a liquid cell, and we attach a transducer to that cell and then apply an RF frequency to the transducer, and that creates acoustic waves, mechanical waves that travel through the material at some velocity v. Now v could be equal to 617 meters per second if it's tellurium dioxide, or it could be as much as 4,000 meters per second if it is lithium niobate, and that gives rise to a wavelength of spatial period big lambda. Now, typical frequencies to excite an acousto-optic modulator might range from between 50 megahertz to somewhere in the neighborhood of 500 megahertz or maybe a gigahertz. Now, we can find big lambda using the expression, familiar, hopefully, expression, big lambda F equals V. So, if we look at an example, let's try to find big lambda given a frequency, a driving frequency of 100 megahertz and a wave speed of 617 meters per second. We just take our lambda F equals V equation, we use it to solve for big lambda, we get 617 meters per second over 100 megahertz, plug it into our calculator, and we get 6 microns. That is the spatial period of the acoustic wave traveling through the acousto-optic modulator. For another example, now let's take it a step further and find the output angle of diffracted light. If light is coming in at 0 degrees, it's red, and we have a 100 megahertz signal at 617 meters per second. So the first thing we do is we find big lambda, just the way we did before. The numbers are actually all the same in this case, so we know that the spatial period is 6 microns. So we'll just put that in our pocket. The next thing we need to do is find the output angle. So the output angle is going to be given to us from the grading equation shown here. We're going to choose the positive +1 order of diffraction. That's m equals +1. And we're going to solve then for the output angle as the arc sine of little lambda over big lambda, plus the sine of the input angle. But we had, in the definition of the problem, said that input angle was 0. That's normal. That means the light is coming straight in at the normal, and therefore it's canceled out of the expression. We just have then the wavelength of light, 633 nanometers, over the grading spatial period, 6 microns. Plug that into our calculator, and we get 6.06 degrees as the output angle. Now, we want to use what we've learned to determine the resolution of an acousto-optic system. That's usually measured in what we call number of addressable angles, or the number of addressable points. And these are actually equal to each other. And the expression is n is equal to delta theta big. That's the total scan angle divided by delta theta small. That's the beam divergence. So what's the total scan angle for a beam? The total beam divergence divided by the total beam divergence. So we can understand this by looking at the Fourier transform. In space, we have light. It's being diffracted by an acousto-optic modulator, and it's being driven at its highest frequency, so it has its smallest spatial period, big lambda, minimum. So as light comes and diffracts, it's going to diffract at its largest possible angle, or the most positive in this case. And the fact that it's a limited beam means it's not going to be just moving in one direction. There's going to be some diffraction, and that's going to give rise to a divergence angle. And the beam width we're going to call delta theta small. And that theta small is approximately, for little angles, this is going to be approximately equal to lambda over big D. This should be familiar. This should be approximately equal to, this is sine theta equals lambda over D from our multiple slit interference equation. Now, let's say that we excite it at the lowest possible frequency. Now we're going to have the other extreme of the deflection. And that total difference in deflection, the total bandwidth of angle, that's delta theta big. That's going to come from the grading equation. So we make the same assumption we did before, that sine theta is equal to theta. Then the grading equation looks like theta out minus theta in equals m lambda over big lambda. We're going to write this twice. One for the minimum spatial frequency, minimum spatial period, and one for the maximum spatial period. Now we can get rid of theta in and m. We'll say that m is just a positive one order. We'll get rid of theta in because just illuminate straight on. We'll call the biggest output angle theta 2 and the smallest theta 1. Delta theta then is just theta 2 minus theta 1, which is equal to lambda times the quantity of 1 over big lambda minimum minus 1 over big lambda maximum. Now, lambda minimum is just equal to 1 over the maximum frequency. So we can replace 1 over big lambda with their respective frequencies. So f max minus f min, all that divided by v. And this is big delta theta equal to lambda delta f, or the bandwidth, over v. This is what we're going to use to find n, which is, as you recall, delta theta big over delta theta small. The total scan angle over the beam divergence. And that is equal to lambda delta f, or bandwidth, over v. This might be, and then the beam divergence is lambda over d. The lambdas cancel out. You get n equals d, that's the illuminated aperture of the AOM, times the bandwidth of the AOM over the velocity of the sound in AOM. Now there's a special case where you say that the lowest drive frequency is actually 0. It goes way low. In that case, the number of scannable points is equal to the aperture times f max over v. And that is just equal to 1 over the minimum spatial frequency. So n in this case is just the illuminated aperture divided by big lambda minimum. That's meters over meters. The units here are actually just number of periods. Specifically, the number of periods in the aperture. So if we take a look at the AOM, what we're saying is the number of scannable angles, or the number of scannable points of an acoustic modulator, is approximately equal to the number of periods that fit in the aperture.